Hey everyone, welcome back to another explainer. Today we're diving right into a high-stakes battle of man versus physics happening deep inside an electric vehicle's motor. We're going to look at exactly what happens when you push an EV to its absolute limits, and more importantly, the incredible layered engineering that stops it from just melting down on the spot. All right, picture this. We are looking at a truly extreme environment. We're talking about temperatures fatally spiking to 150 degrees Celsius and short-circuit currents hitting a massive 1390 amps. Think about when you slam the accelerator for full torque or aggressively climb a really steep hill. The motor is suddenly subjected to immense physical, electrical, and thermal stress. If the cooling system is even slightly degraded, all that energy literally has nowhere to go. So how exactly does modern engineering prevent total catastrophe? Well, we're going to track the progressive layers of defense across 5 key stages. First up is the threat, or root cause analysis. Then the brain, that's the software and hardware diagnostics. After that, we look at the blueprint, focusing on DFMEA design defenses. Then the build, checking out PFMEA process controls. And finally, the crucible, which is our DVP&R extreme validation.
Let's jump right into Section 1, the threat, focusing on root cause analysis.
So what actually happens when you demand that extreme torque? Boom, massive phase currents generate severe local heating, something engineers call Joule heating. And this attacks the motor on 3 fronts, like a triple threat. First, it pushes the stator core and windings way past 130 degrees Celsius. Second, it fundamentally alters the motor's electrical properties. And third, when you combine all that heat with high-frequency vibrations, this thermal fatigue actively degrades the insulation and seals. That invites oil and moisture right in, creating high-impedance short circuits. Now, this is where it gets really interesting. Heat creates this hidden killer where the physical properties change so much that the software essentially loses track of reality. Engineers call this parameter drift or model mismatch. Extreme heat can increase the stator's copper resistance by 30 to 40%. It can even double it in some cases. At the exact same time, the permanent magnets suffer thermal decay. This creates massive calculation errors. The software thinks the motor is in one state, but the physical hardware is doing something completely different. That leads to control vector misalignment and, potentially, the permanent demagnetization of the motor. It's basically flying blind. Moving right along to Section 2, the brain, looking at software and hardware diagnostics. To counter this threat instantly, this system relies on an ultra-fast diagnostic brain operating in mere milliseconds. It's a brilliant example of a layered defense system. On one side, you have a strict hardware tripwire. The motor's temperature sensors send an analog signal to the main control chip. If that signal falls outside a super tight 0.5 to 4.5 volt window, a hardware comparator flags a wire break or short circuit in microseconds. No hesitation. Paired with this is the software side, acting like 2 co-pilots, continuously verifying flight data. It uses a Model Reference Adaptive System, or MRAS, to estimate resistance in real time. And that's entirely backed up by a dual-core doer-checker lockstep verification to ensure high temperatures haven't corrupted the actual data. So the crucial point here is an intelligent escalation strategy. It functions perfectly as a controlled pressure release valve. If things get too hot, the system doesn't just instantly shut off while you're cruising on the highway. That would be incredibly dangerous. First, it triggers thermal derating, entering a limp home mode that smoothly limits your torque at a rate of 500 newton meters per second, dropping down to about 30% power to reduce that Joule heating. Now, if that's still not enough and it detects a total loss of control, it initiates a secure mixed adaptive shutdown within just 60 milliseconds to vent extreme thermal energy safely. All right, Section 3, the blueprint, covering DFMEA, design defenses. How does this look in the design phase where vulnerabilities are eradicated before manufacturing even starts? Well, consider this patented search coils innovation. It's absolutely remarkable because it physically bypasses temperature interference. It guarantees precise motor control even when the primary sensors are completely overwhelmed by heat. By replacing standard sensor wiring with this specialized search coil design, the position feedback is electromagnetically decoupled from the main motor windings. Translation, no matter how hot the motor gets or how much that state or resistance doubles, the control module is still getting a pristine, interference-free reading of the motor's position. Engineers also had to tackle the intense thermal stress of an active short circuit, or ASC. A standard ASC dumps all that massive short circuit current and heat into one concentrated spot. That's a recipe for disaster. But by actively alternating the electrical short between the upper and lower components of the inverter, the alternating ASC strategy distributes that thermal dissipation evenly. It's actively monitoring the temperature, and if it approaches the 130-degree material limit, it just shares the load. This prevents any single power module from melting down under stress. It's a very clever workaround.
Up next is Section 4, the build, focusing on PFMEA process controls.
Flawless blueprints demand flawless execution, right? This means absolute total automation on the assembly line to eliminate human error. Manual assembly of temperature sensors is completely banned on these lines. Instead, 3D automated robotic dispensers apply highly thermally conductive adhesives, immediately followed by automatic optical inspection to guarantee 100% coverage with zero air pockets. Then, they lock in incredibly strict pressure and temperature curves during the vacuum pressure impregnation, or VPI curing process. This ensures the insulation resin has absolutely zero microscopic air bubbles, completely eliminating the risk of high voltage breakdowns when temperatures spike. Finally, the connections are made with precision crimp heights to create ridiculously dense cold welds. And here's a fascinating little detail for you. To stop high-frequency vibrations from microscopically destroying the electrical contacts over years of driving, they robotically inject a tiny amount of highly specialized grease called Neogel 760G. Extreme heat and vibration cause a phenomenon called microfretting, which oxidizes contacts and causes electrical resistance to spike. But this specific grease contains copper passivators and a fluorosilicone base. It forms a continuous oil film that entirely blocks oxygen and condensation from entering the connection, keeping those electrical pathways completely perfect over the entire lifespan of the vehicle. Finally, Section 5, the crucible, our DVP&R extreme validation. Before anything gets approved for mass production, it goes through absolute torture. Engineers simulate the definitive worst-case scenarios. They take the entire motor assembly, mount it onto a massive shaker table, and violently shake it with 3-axis wideband vibrations ranging from 10 to 2,000 hertz. And while they're shaking it, they continuously swing the environmental temperature from -40 degrees freezing to 150 degrees boiling Celsius. They do this non-stop for over 300 hours. To even pass, the insulation resistance has to remain at or above 100 megaohms, and the contact resistance cannot increase by more than a microscopic 1.2 milliohms. But the ultimate proof? That's the demagnetization and algorithmic takeover test. Engineers deliberately run the motor at a blistering 12,000 RPM under a maximum heat load of over 130 degrees. Then, they just intentionally sever the physical sensor connections, literally cut them off. The backup software has to realize the sensors are gone and seamlessly take control using those patented search coils and algorithms in under 5 milliseconds. And it has to do it with less than 5 Newton meters of torque fluctuation. They also trigger a high-speed active short circuit, just to prove the system can clamp the peak voltage below 720 volts and the current below 550 amps, without causing any irreversible demagnetization or physical burning to the magnets. It's absolutely wild. It is just an absolutely stunning orchestration of hardware, software, and manufacturing precision. So the next time you accelerate onto the highway and feel that rush of power, take a moment to appreciate the incredible symphony of layered engineering that is tirelessly defending your vehicle behind the scenes. It's not just a motor spinning, it's a triumph of science keeping the brutal forces of physics firmly in check. Thanks for joining me on this explainer, and we'll catch you on the next one.